Hello everyone, welcome to the next session of solutions chapter in this about colligative properties. So let's see one by one what are colligative properties and how does the vapor pressure and amount of solute changes these properties. That will be the topic now. So colligative properties are these. Okay, first property is relative lowering of vapor pressure of the solvent. Second is depression of freezing point. So here the vapor pressure of the solvent is a colligative property. Freezing point of the solvent is another colligative property. So what happens when you add a solute, it actually decreases. So depression of freezing point, elevation of boiling point of the solvent, and the last property is osmotic pressure of the solution. Now all these properties depends on the number of solute particles. Okay, so whatever you add, that is solute particle, irrespective of their nature, okay, relative to the number of particles present in the solution. So basically it just depends on the number of solute particle that you have put in. That's why we call them colligative property. Now let's focus on the first property, that is relatively lowering of vapor pressure. Now if you remember in the last session I discussed about this graph. Okay, so this graph is telling vapor pressure and this here is the mole fraction. So if you see, whenever you add a non-volatile solute, what happens? The vapor pressure decreases. Okay, and this was actually given by Raoult's law. So on this equation and P1 is equals to P1 not X1. Okay, now we will try to see how the amount added of the solute is going to affect the lowering of vapor pressure, like how much will be the pressure getting lowered. Now so if you have noticed, mole fraction and the vapor pressure of the solvent will be this, that is P1 is equals to X1 P1 naught. Now if you see, the vapor pressure is getting reduced, so reduced vapor pressure will be P1 naught minus P1. Okay, where P1 naught is of that of pure solution. Okay, there was no solute particle inside, so the difference is actually your vapor pressure difference or reduction in vapor pressure. So this P1 can be expressed as X1 P1 naught. So X1 P1 naught, you can take out P1 naught common, and this is the value. We know that X1 plus X2 is actually equals to 1. So we can write down 1 minus X1 as X2. Simply delta P1 is X2 P1 naught. So delta P1 divided by P1 naught is going to be your X2, right? So here this is actually relative lowering of vapor pressure. So relative lowering of vapor pressure is actually equal to X2. Okay, what is X2? X2 is actually the mole fraction of the solute particle. Relative lowering of vapor pressure is equal to the mole fraction of the solute. Now if there are more than two components, okay, like for example if there are 3 4 5 components, so this part here will be submission of all the mole fractions of solute particles. Now here I can write this, because X2 is what? Mole fraction. That means number of moles of second divided by number of moles of all the components inside. Okay, this is the value of X2. Put that, this is the scenario. Now assume that you have added very little amount of solute. Okay, if the amount of solute is very low, N2 is far less than N1. So you can ignore the value of N2 in the denominator and simply write N2 by N1. Remember that this is approximate, valid only for dilute solution, whenever the solute particle is very low in quantity. And then later on you can express the number of moles as given weight by molecular weight, given weight by molecular weight. So if you want to calculate molar mass, this is a perfect equation. You just measure the relative lowering of the vapor pressure and equate it to this, you will get your molar weights. Okay, now let's go on to the next colligative property, that is boiling point. Here what happens is elevation happens of the boiling point. Now what's the definition of boiling point? So when we were kids we were having some different definition. Now we will follow a different definition, that is this one here. Okay, So liquid boils at a temperature at which its vapor pressure is equals to atmospheric pressure. Note down, liquid boils at a temperature at which its vapor pressure is equals to atmospheric pressure. Because what happens, let's say the atmospheric pressure is 1 atm. So whenever you have a let's say solvent, it if you increase the temperature, slowly vapor pressure, as soon as the atmospheric pressure is equal to it, the liquid whatever you had is going to go in the atmosphere, right? So vapor pressure is actually equal to the atmospheric pressure. That is the new definition that you have to know. Now, from the previous colligative property, we know whenever you add a solvent to whenever you add a solute to our solvent, the vapor pressure gets decreased. So you see the vapor pressure has decreased. So if you see here, you need much more amount of temperature to achieve 1 atmospheric pressure. Okay, so this here is representing your um, temperature on the x-axis. So TB naught was that of the pure solvent. TB is that of the solution, boiling point of solution. Difference between the two is delta TB. That is your elevation of boiling point. Now, so this is here. Okay, so we saw the definition. We also know that vapor pressure of the solvent decreases in presence of a non-volatile solute. Now, here you should note that the elevation of boiling point, it depends on the number of solute molecules rather than their nature. Again, we will do the derivation. So here, this is P minus B naught, which is actually delta TB. Now, delta TB is the elevation in boiling point. So this elevation of boiling point for dilute solutions, it is again proportional to M, where M is molality. Please note down where M here is molality. So in order to remove this proportionality constant, you can proportionality constant sign, you can introduce a constant Kb. So delta Tb is equals to Kb times M, where Kb is your boiling point elevation constant or molar elevation constant. The units of Kb are in Kelvin kilogram mole inverse. Okay, remember that this equation is again valid for dilute solutions. A dilute solution means we are having less amount of solute inside. So molality, number of moles divided by weight divided by the per kg of solvent. Just express value. You write down this. If you express it here, you can and calculate the you can calculate if you put it here, you can calculate the molecular weight of the solute particles. This is one of the techniques. Calculate M2. The other are known, some numericals based on this all our class. Now, next colligative property is depression of freezing point. Okay, so let's say that this is your frozen solvent, this is your liquid solvent. We know whenever you have added an solute particle, the vapor pressure decreases. So this is your solution, always lies below the solvent. So if you see, you need more lower temperature to freeze the solution as compared to the liquid solvent. Now, also note down the definition of freezing point of a substance. It is actually defined by the temperature at which vapor pressure of the substance in liquid phase is equal to its vapor pressure in solid phase. Okay, so this is the new definition. So here also we do the same calculation. Okay, so what we do is actually delta TF, that is actually TF naught minus TF. You can, this here is TF naught, this TF. TF naught minus TF is the depression of freezing. This here again is proportional to your molality. Just put the value. That's the scenario. We introduce a constant Kf, which is known as freezing point depression constant or molar depression constant. Again, you can express molality as number of moles of solute divided by kg of solvent, and you can express this M here, and you can find M2, that is the molecular weight of solvent. So that's it in this session, guys. Okay, I hope you guys enjoyed. In the next session, we will be looking at another colligative property, that is the osmotic pressure, and then we will see what happens when we are talking about dissociation and association. Guys, thank